So before I start, I want to make two comments. So one is that first, one thing I want to do is to, thank the people that really, well, apart from you, of course, that without you there is nothing, but the people that help the course be successful to the extent it's successful, which is the tutors, Anna. She's the one that tells me, well, she's the boss, so she tells me what to do and not to do. And I also want to thank, I guess, the tutors for this course, which is Eduardo and Joel. Eduardo has been putting a lot of effort in turning the lecture notes that Catherine wrote down last year into and improving them. So thank you for that. And the other thing I want to say is that, as you can see, my voice is not completely. First of all, can you hear me? I can barely hear myself. So, so if people were hoping to have an ultra marathon lecture today, I'm afraid that it will not happen because my voice will die along the way. So I'll try to keep it in a finite, not too long amount of time. And for the one or two people that would have liked the marathon, I'm sorry about that, but I think I won't be able to do it. Okay, so let's try to complete today our discussion of minimal models and how to compute correlation functions in minimal models, in particular for the Ising model. But before we go there, is there any question about last week? No? So let me remind you where we were. So the thing that we saw yesterday on Friday was that the tensoring or fusing representations of the Virasoro algebra which have a null vector in them are truncated, okay? So remember that we wrote down, so we looked explicitly in the case of a level 2 descendants. So remember these are states that on the one hand are descendants of some primary, but they're also primaries. Okay, so it means that they're annihilated by the positive frequency Virasoro generators. And at level 2, we constructed explicitly the two null vectors that can appear by essentially solving this condition. We found that there are two possibilities. Chi can be this very specific linear combination. Okay. And in solving this equation for L2, you get a quadratic equation for H, which is the scaling weight of the associated primary. And the two possible solutions to these equations are for H equals H1,2, sorry, or H2,1, okay? Where if you remember this H12 and H2,1 are the scaling dimensions at which we found a zero in the matrix of inner products of the level 2 descendant. So in an earlier lecture, we computed the matrix of inner products of all states that had weight 2, and we computed the determinant of this 2x2 matrix, and we factored it. We found that it had three zeros. It's a degree 3 polynomial. One zero was at 0, and the other one was precisely at these values, okay? So we get a null state precisely at the value of H at which the determinant has a 0. And that makes sense because one of the things that you prove was that if you have a state which is a null state, so it has both these properties, it has zero norm, okay? So a null state is associated in particular with a eigenvector of the matrix of inner product that has zero eigenvalue, okay? And those happen with eigenvalues h12 and h21, okay? So that's why these are the numbers that appear. And what we saw is by demanding, so one thing that you also showed is that these null vectors are orthogonal to everyone or to all states in the representation. They have zero norm and they have zero overlap with everyone else. And that gave rise to this important equation, the null decoupling equation, null vector decoupling equation, which is the operator counterpart of the statement that a null state is orthogonal to everyone, which was that the corresponding operator, chi of z, which creates, let me call it W, that creates this corresponding null state, has a zero correlation function with everyone else, with any other operator, in particular two primaries, okay? And then we were using the, okay, so this had to vanish. That's the statement that chi is a null vector in the operator language. And from here we derived a differential equation for the correlation function. So this guy is the primary associated to the descendant chi. And then we have these other two primaries. Okay, and for this particular case that we're talking here, which is the level 2 descendant, this phi rs was essentially either phi 1, 2 or phi 2, 1, okay? By this, I mean this is the primary that creates a state from the vacuum with a scaling weight h1 half or h2, sorry, h1, 2 or h2, 1. I will write later explicitly, even though I already did in the past, but what the formula for this HRS is for arbitrary levels, and it's just a function of the central charge of the conformal field theory, okay? And essentially what we saw is that we can straightforwardly write down the differential operator associated to this null vector because we know explicitly what the null vector is. Then we use the operator state correspondence, and we got a specific differential equation. And from here we derived this truncation business. Sorry. So what we saw is that if you tensor the primary that has a null state at level 2 with an arbitrary primary of the Virasoro algebra labeled with momentum alpha, which I'll remind you what it is, you get two possible representations. You get alpha plus, you shift the momentum of this representation by alpha plus in the positive direction or in the minus direction, okay? Likewise, if you look at the other primary that can have a null vector at level 2, you get a similar shift, but now with respect to different quantity, which is alpha minus. Where I remind you that alpha is just a clever parameterization of the scaling weight of the primary here. So phi alpha, acting on the vacuum, creates a primary with weight H alpha, okay? And H alpha has some constant piece like that, and then something that looks like the scaling weight of a momentum operator, okay? That's why I call it momentum, shifted momentum, okay? And alpha plus and alpha minus I'll write later. It's essentially some specific function of the central charge, which I'll write in a minute, okay? So this so far was just a reminder of what we did last time. Now we want to go further. Now from our analysis of the determinant of matrix of inner products, it is clear that there are null vectors, namely zeros of the determinant of that matrix at arbitrary level, okay? And now what I want to show, or at least sketch, is how primaries, so that's one important statement that I want to make, that have null descendants close upon fusion, okay? So this is just a statement that if you start with primaries that have a specific null vector in its representation, sometimes it's called a module, and you tensor those primaries, you will get another linear combination of primaries on the right-hand side that will have null vectors in the representation, okay? And that's very important. And it's the key to get into the minimal models, okay? So now let's see where the null descendants or null vectors appear. The way to discover them, the simplest way, is to look at this matrix of inner product for arbitrary level. That's something that's for arbitrary level, for any given level, it's straightforward to do. We did it in the Blackboard for level 2. For level 3, you would have to look at a 3x3 matrix and compute its determinant and look at the zeros as a function of the scaling weight. To prove it in general, you need, it's more complicated, but this is something that is a very important result in the subject that was proved by Victor Kac. This is the same Kac that you might have heard in the context of Kac-Moody algebras. What he found essentially, okay, let me show it this way. He essentially found the zeros of this determinant, of this matrix, okay? The zeros of this matrix will be in one-to-one correspondence with states that have zero norm. Some of them will be precisely associated to these null vectors. Some others will be associated to the descendants of null vectors, because remember that I said that if you have a null vector, the descendant of a null vector is also null, okay? It has zero norm, okay? So what he found is that this determinant has this factorization. So up to some positive constants that we don't care about is the product over a pair of integers, Rs, such that Rs, the product of Rs is smaller or equal than n. N is the level of the descendant. So this matrix has partition of n times partition of n dimension. So it's a big matrix. Remember that we said that the number of states at level n, when you count them, is given by the number of partitions of n. So for 2 was 2, for 3 was 3, for 4 was 5, I think, and so on and so on. So this grows very fast. And by doing kind of an analog of the calculation that we did, but in a fancier way for level 2, he finds this formula. So you get a polynomial in H. These are the zeros of the polynomial, and they have some degeneracy. Okay? Where this P and S, P as a function of n minus Rs is the number of partitions. So what I want to say is that P of X is the number of partitions of X, okay? So some of the zeros are very degenerate, have high degree. And this has to do precisely, if you think about it, has to do with precisely the fact that if you have a descendant, say, at level 2, you have a descendant at level 2, now go to level 3. There will be new states that will have zero norm. This will be associated to the new null vectors, but you will have a state of zero norm that you already knew about, which is just L minus 1 acting on the level 2 descendant. That also has zero norm. And that's why you get this degeneracy factor, okay? Now, where are the locations? So of course, this guy vanishes if n minus Rs is negative, of course. Okay? Now, the thing that we're really interested in is the analog of the exact location of the zeros. So I want to know the formula of HRS, which are the values of the scaling weight for the primaries that have null vectors at level n as a function of the central charge. So it has a formula like C minus 1 over 24. plus 1/4. And for level 2, we worked out this explicitly by just computing the determinant. Plus S alpha minus square, where alpha plus and alpha minus are two convenient to define functions of the central charge. The square root of 1 minus c plus minus the square root of 25 minus c divided by the square root of 24, okay? So this amazing formula, it tells us precisely where the null vectors in representations of Vidal Soro algebra can appear. They can only appear if the primary has these very specific values of h, okay? And the number of null vectors at level n is given by the number of ways that you can take a pair of integers such that the product of r times s is n, okay? So at level 2, there are two ways. You can write 2 as 1 times 2 or 2 times 1. At level 3, so at level 3, how many we can have? We can also have only 2, because you can write 3 as 1 times 3 or 3 times 1. At level 4, there are more ways, and you can try to count how many there are. But this formula just gives you a complete way of characterizing where the primaries that have null vectors lie, what values of the dimension they must have. And the statement that they are closed under fusion, so I want to keep, if I forget and I erase this blackboard, stop me, okay? Because I will need it later. Now, the thing that's amazing is that if you look at this formula that I wrote about the fusion here of how phi tensored by a primary of dimension h alpha, where alpha is the momentum, we can immediately see already a very nice result, which is that if we take a level 2 descendant and I multiply it by a level r times s descendant, you get another primary which has null vectors in them, okay? So that's for the 1, 2. If I look at the 2, 1, it will be exactly the same. But now the shifts will be on the first index. What this formula is telling us is that if I start with 2 primaries that have null vectors in them, and I fuse them or tensor them, I will get primaries that also have null vectors in them, okay? So that means that these primaries that have null vectors in them are very special. They close among themselves. Note that in general that's not true. For arbitrary alpha, that's not true. But for these very special values of the dimension, it's true. They close. So the slogan here is that they close upon fusion or tensoring. And you see that this follows directly from the formula that we derived in general there, and for the explicit formula of HRS that we write here, okay? Notice that a shift by alpha plus in the momentum is exactly the same as shifting R by 1 or minus 1, okay? That formula? Good. And now this looks very much like something that you know very well, which is the way you fuse representations in SU2. So this looks like fusion or tensoring of SU2 representations. Because if I take now the tensor product of a representation that has spin J1 with a spin J2, as you know, you get the sum of spins from J1 minus J2 to J1 plus J2, phi J3. And this rule is exactly the same as this rule, where now I just chose here for J1 the spin 1/2 representation, okay? And it's especially this rule if you just know, if you think of R or S as the dimension of the representation, so as 2J plus 1. Okay? So this rule at this level is exactly like the tensoring of G2 representations, where I identify the spin as with R and S by this formula. Is this clear? So of course, since this is like SU2, if I start with the spin 1/2 representation, I can get all the other ones by just multiplying it many, many times. But this will never stop. I will get an arbitrary high spin just by multiplying more and more. Now, the thing that's amazing in the study of Virasoro representations is that so far these null vectors appear for an arbitrary value of the central charge. I haven't told you what the central charge is yet, okay? Now, the thing that's remarkable is that this product actually truncates into a finite dimensional set. So right now, this is just an infinite dimensional set, just like SU2 has an infinite number of representations of an arbitrarily high spin. But what I want to say is that that the product truncates if we choose the central charge, which is one of the fundamental characteristics of that labels the conformal field theory. If I take it to be 1 minus 6 p minus q squared divided by pq, with pq being relatively prime, okay? So and then you get a finite number of primaries. So now let's see how this happens a little bit. So how can I show you this? Yeah, so another way of writing this equation is equivalent. This choice of central charge C that I wrote here is equivalent to saying that there exists relatively prime integers PQ such that, let me write it carefully, so P alpha minus plus Q alpha plus equals 0, okay? So alpha plus and alpha minus are these two functions of the central charge that we wrote here that appear in our formula for the scaling dimension for a primary that has a null vector in it. Now imagine that such a pair of relatively prime integers P and Q exists. Now, by looking at this formula, what we find quite immediately is this. Right? Do people agree with this formula? If P alpha plus Q alpha, sorry, P alpha minus plus Q alpha plus is 0, it means that if I shift here R by Q and S by P, this formula is invariant, right? Do you agree? Okay. So that means that we can impose equivalence relation that says that, so this is the RS axis. So we have the label by integers, right? So what this formula is saying is that we can impose an equivalence relation such that when we hit the boundary, so that when R goes to Q or S goes to P, we identify it with an operator inside this quadrant, okay? So that means that we can restrict our attention to a finite set of operators that live in this quadrant, where this is, I guess, P, and this is Q. Okay? Furthermore, it follows from this equation that the following also formula holds. There's a reflection property that HRS is the same as HQ minus R, P minus S. This also follows quite immediately from this formula. I mean, just verify it with your own eyes, that if you plug in there R, you map it to Q minus R, and S to P minus S, that the formula is invariant, okay? This gives a further equivalence relation that you can impose. If I had color, but I think I do. Essentially, it tells you that you can further restrict your attention to one of these regions. Say, this one or this one, okay? In the operator language, what this means is that you identify phi RS with phi Q minus R, P minus S, okay? Where, due to this identification, R it goes from 1 to Q minus 1, and S goes from 1 to P minus 1, okay? So let me recap. The statement was that we had this general fusion rule. We noticed that for a very specific value of the central charge, the fusion rule truncates by making this equivalence relation, because the dimension of this guy is the same as this guy. And therefore, under this equivalence relation, we're left with a finite number of operators, okay? And the number is precisely the number of points that live inside this triangle. So the number of primaries is 1/2 P minus 1, Q minus 1, okay? So conformal field theories that have this property, namely that have this value of the central charge, very specific value of the central charge. Notice that this implies that C is less than 1, okay? And that have this spectrum of primary operators labeled by this pair of integers subject to this relation. This is what are called the minimal models in two-dimensional conformal field theory. And these are the ones that we can solve completely. Let me stop a second. Yes?
Can another choices for C and give the same finite set of...
No, it is unique. So this is the only value of the central charge for which the primary is truncate to finite set. That's why it's very special. Now you can have CFTs in higher dimensions that have primaries with null vectors in them, but typically those CFTs have an infinite number of other primary operators, just not a finite set. For a finite set, this is it. So that's why they're called the minimal models.
But this is like the only choice.
The only choice. Yes.
Why should there be only one operator associated with every H where the determinant vanishes? Why couldn't we have the whole family of phi RS?
What's the question? So you're saying why do I impose this equivalence relation?
No. Why are the operators that we use, uniquely labeled by the pair RS?
Because, I mean, we know where all the zeros are. And the zeros are labeled by RS.
Okay, but why can't there be more operators associated with a particular zero?
No, because this gives you all the zeros. And I said, and we know where the zeros come from. They either come from, so imagine you're at level n. A zero in the determinant at level n either arises from an operator phi rs, where rs equals n, or it arises by acting with the Virasoro creation operators on another null vector at level r prime s prime, where the product of r prime and s prime is less than n.
So it's because of the operator state correspondence that we associate one operator with every null state.
Yes, I mean, yes. I mean, talking about states or operators is completely equivalent in CFT. So now I want to stop and, at the moment, at what this result actually implies. So let's look at this amazing formula. So this is quite spectacular, I would say, because this is a formula that tells you, without ever talking about a Lagrangian or a Hamiltonian or anything, the exact spectrum of dimensions of operators in a CFT, okay? Now, if you did one of the problems earlier in the year, which I think was optional, so the problem is that not many people did it, you were asked to compute, say, in a particular theory, the anomalous dimensions at one loop for a scalar field theory that had a phi-cubed interaction. And you saw that even computing just at one loop, the leading correction to the classical dimension was a bit, it's not difficult, but you have to work a little bit. This is to be compared with this, where this gives you the answer completely resummed. Okay? There is no parameter here. This just gives you the exact answer to that expression. Another we used was very simple physical criteria and basic properties of the Virasoro algebra. Okay? Notice that these numbers also would be very hard to get from any perturbative analysis. These numbers are very far away from things that you would compute by naive dimensional analysis. So for example, these are quantities that if you try to start from a Lagrangian description, it will be very hard to get because the theory will become very strongly coupled. So let me give you an example of that. So let's look at again at the Ising CFT. So this was the model for 3, okay? Here we had 3 primaries, the identity, the energy, and the spin operator. So 1, 1 was the identity. The 1, 2 was the spin. And the 2, 1 was the energy operator. And by plugging in the value of Q and P into these formulas, well, remember that I already said that this central charge, this conformal theory has central charge 1/2. And now applying here the dimensions of the corresponding operators, you find that this guy has dimension 0. I mean, that you knew. The identity operator has dimension 0. The 1/2 has a very strange dimension, 1/16, which will be very unusual from the point of view of any dimensional analysis. You never get 1/16 if you do a naive dimensional analysis of dimensions of operators. And this guy has dimension 1/2, okay? Okay. This is to be compared to the naive way you would study the Ising model, and people did study the Ising model in the 60s and 70s, which was using this Landau-Ginzburg criterion, where you write down a low energy effective action for the basic variable in the system. In the Ising model, the basic variable that you want to model is the magnetization. You want to study the properties of the magnetization as a function of the temperature. And the Landau-Ginzburg description. So this is to be compared with the semi-classical Landau-Ginzburg description, where you write down an effective field theory for the ordered parameter, which is the magnetization. And the ordered parameter for the magnetization is just a scalar field. Now, the Ising model has a Z2 symmetry, right? You can map all spins to minus itself. And that's reflected into the fact that the potential is quadratic, okay? So this is the naive description that you would start if you want to study the Ising model from a continuum field theory point of view. You're now at large distances where you don't see the details of the lattice. All that you know is that there is a magnetization field that varies in the lattice. And that's actually the Ising CFT, and people did study this. Notice that the dimensions here, so the point is that this operator in 2 dimensions, this field theory in 2 dimensions, both this guy and this guy are very strongly relevant operators, okay? So that means that they flow like crazy. So if you start at some Gaussian fixed point with this guy is tuned to be 0, and you turn on a small non-zero value of the parameter, this guy flows very, very fast as a function of the scale. It's not logarithmic. So remember that in QCD, for example, or lambda phi to the 4 in 4 dimensions, the coupling constant lambda, for example, decreases logarithmically in that case with the energy scale, or with the renormalization group parameter. Here it grows incredibly fast because phi has a naive dimension 0, okay? And the universality class is described by a non-trivial fixed point that in some sense is very far away from the original Gaussian fixed point here. So I'm giving you a physical argument of how this conformal field theory arises from the textbook where you would describe a magnet in 2 dimensions, fixed point. Because phi is highly relevant in 2 dimensions, you flow very fast to another CFT, which is non-trivial because as you grow here, from the point of view of these degrees of freedom here, this theory is very strongly coupled because the coupling grows very, very fast in the infrared, okay? It's very strongly relevant. So studying the properties of the CFT here using the Lagrangian here is a very bad idea because perturbation theory is completely breaking down. That's a problem in life. I mean, sometimes perturbation theory doesn't work. That happens in QCD. If you want to study what happens at the energies of the nucleon, it's fine in the UV. And the point is that even though we do not really know how to describe this CFT or compute in this CFT directly using this Lagrangian, the physical picture is that this CFT is just this CFT, this Ising CFT. So here we just compute directly on the nose what happens here. But physically what it's really doing is following the dimensions of all operators exactly all the way to the infrared fixed point, okay? And this is very powerful because even if you had an infinitely powerful computer and you could follow this in the infrared, it would be very hard to do. Here we just got all the numbers, and not only for the Ising model, we got it for an infinite number of models. We got exactly the numbers from the beginning. We didn't care about strong coupling or anything, okay? And that's one of these examples where few examples in physics where just using very simple criteria and some assumptions you can get directly to the exact answer, okay? This is the kind of thing that we would love to be able to do in 4 dimensions. So start with QCD, and you want to study something in the deep infrared where the theory becomes strongly coupled, or can flow to a non-trivial conformal field theory, depends on the physics. We would like to be able to study the theory directly here without worrying about the fact that there's some UV Lagrangian at high energies that is becoming strongly coupled, okay? Last thing I want to mention about this, it might be a marathon after all. Is that this fixed point, in this respect, is very different than the Gaussian fixed point we described when we did the 4 minus epsilon expansion, if you remember. So there we described that in 4 dimensions, you could find a non-trivial fixed point by in D equals 4 minus epsilon by killing off the leading classical term, the fact that phi to the 4 in D in 4 minus epsilon has dimension epsilon with the 1 loop term. So we had a fixed point, a 0. Remember, the fixed point is a 0 delta function at lambda star equals epsilon. The thing that was very different in this case from this case is that here this fixed point could be at arbitrarily weak coupling. So that means that that fixed point in this picture would be very, very, very close to the original Gaussian fixed point, okay? So you could use perturbation theory. As you go to lower dimensions, since you have strong infrared fluctuations, the fixed points that you get in lower dimensions are always very far away from the Gaussian fixed point, and that's why they're hard to study, okay? And that's why this whole subject of conformal field theory changed the whole field of critical phenomena and strong coupling dynamics in lower dimensions when it was invented in the 80s. By the way, something I recommend that you do if you're interested in this subject. I just happened to look again this morning at the paper. So the seminal paper where all of this was done is a paper by Belavin, Polyakov, or Russian, Zamolodchikov. This is really an amazing paper because essentially they did everything in it. And the thing that's amazing that I could check this morning is that the paper is completely readable. So I think that if you actually try to read the paper, you will understand 90% of it now. And I recommend that you do, because as you move from this mode of being a student to being a researcher, you will have to get used to reading papers. But this is a very good paper to read because it's really very readable. And you may find more details than I have time to give in the lectures about all these CFTs, how they were constructed, also the history behind it, and so on. It's in some nuclear physics B. But if you write this name in Google, this paper has like thousands and thousands of citations. So, I mean, you will find it. Cool. And it will make me proud if someone actually tries to read it and almost understand it. It would be nice. OK. So this was just a detour to, so we're all excited about this result. Yes? Well, so there's a lot of there is circumstantial evidence for it. So here, you cannot really study the flow. You cannot really do it. But here, by solving the CFT, you can compare with the exact solution, which is a mess of the lattice Hamiltonian, and you can compare everything in detail. By the way, you asked last time, so now let's answer it. So these operators in the CFT are dual to operators that you write down in the Hamiltonian of the Ising model. So we identify this operator as the operator that changes the energy of the bonds in the Ising model. We identify this operator as turning on a magnetic field in the Ising Hamiltonian. And this guy was an idiot, didn't do anything. But as you said, there are many other terms you could write down in the Ising Hamiltonian. For example, the Ising Hamiltonian only has, the standard one that we write down has only nearest neighbor interactions. But now you can have next to nearest neighbor interactions, okay? So can someone guess how to describe that in the CFT? Precisely. And one way to think about it is that the descendant, for example, L minus 1 is essentially a derivative operator, right, in the continuum. So if you act with L minus 1 on a nearest neighbor interaction, it will mix a nearest neighbor interaction with next to nearest neighbor interaction. Okay? So the descendant correspond to generate all other possible spin interactions in the Hamiltonian. Because, I mean, are all descendants relevant? Irrelevant or relevant? Is there any descendant that's a relevant operator? People know what those words mean, I hope. But
Are all these marginal?
that's what I'm asking. No, so these guys are definitely not marginal, right? What are these operators? Okay. They're relevant. I mean, marginal would be an operator that has h equals 1. Well, this doesn't have h equals 1. It's more than 1, that's why they're relevant. They grow in the infrared. Sorry?
Like if we have two derivatives of the primary. So we have those one is the Lagrangian with dimension 2. So we have two derivatives, the dimension of the field would be 2. So this the constant would be marginal.
For which operator would be marginal?
For level 2, we have two derivatives.
No, but, so, okay, this was supposed to be a very simple question. So how do you create the level 1 descendants? The level 1 descendants you create by acting with L minus 1 on one of these guys, either sigma or E, right? So what is the dimension of this state? Sorry? Well, I have an n here. Yes, will be n plus 1/16 or n plus 1/2. But n is bigger or equal than 1, right?
Why does marginal correspond to 1 and not 2 if we are in 2 dimensions?
Sorry?
Why is the dimension of the marginal operator in 2 dimensions 1 and not 2?
Okay, because, so here I'm talking about diagonal theories. So they have h equals h bar, and the dimension is h plus h bar. No, so the thing that really matters, if you look at non-diagonal theories, is delta, of course, which is h plus h bar. But aliasing model is a diagonal theory where it's the same on the left. So what this says is that any descendant, since the energy of L minus 1 is at least 1, acting on any non-trivial primary will have higher dimension than 1, and therefore it's irrelevant. Okay. So now we have determined the spectrum of dimensions exactly in the Ising CFT. So let me write it in the operator language. Has this interesting fall-off behavior, power law behavior. And from here, you can, by doing a fairly straightforward relation between energy and spin and so on to the thermodynamic quantities that we defined earlier in the lecture, like magnetization, susceptibility, correlation lengths, and so on, you find here that the critical exponent associated to magnetization is 1/4. This to be compared to the very naive answer that you would get in the classical theory would be 0. Because the dimension of sigma in the classical theory, which is 5, is 0. And from the energy operator, remember that I said that the energy operator is the operator that pushes you away. If you turn it on in your Hamiltonian, it deforms you away from the critical point. So it changes the temperature. And therefore, it's exactly the operator that knows about the correlation length, okay? Because by tuning it, you go to the critical point. It has infinite correlation length. So from here, you find that the critical exponent nu that I defined earlier in the lecture is 1, which is the one that tells you how the correlation length diverges as a function of the critical temperature. Okay? There were more critical exponents that you can define in the Ising model, but strictly speaking, the two independent ones are only these. The other ones satisfy what I call scaling laws, which just tell you that there's some linear combinations between them that you can write in terms of the two independent ones, which are eta and nu. Of course, you could have used another basis, but these are the two independent critical exponents of the Ising model. Okay. Good. So now what we've done is to find the spectrum of scaling dimensions of the Ising model. Another way of saying this is we've computed the 2-point function. Now what I want to do in the rest of the lecture, if my voice allows me, is to compute the higher point functions in the Ising model. Okay? So here, what we're interested in is in the question of, given that the spin here and here at 2 different points are by this, what is the amplitude that the 3 spins are correlated by one spin being at Z1, Z2, and Z3? This would be for the 3-point function. So this higher point function describes correlations of spins at different space-time points. OK, before doing that, let me remind you that one of the consequences of doing this gymnastics here is that we can derive the fusion rules for the Ising model. So let's write them down. I already did last week, but let's remind ourselves. So Ising CFT. So this essentially tells you who appears in the product of the 3 representations that you can have. So we found that sigma with sigma gives you the identity plus epsilon. I mean, this you can just derive from this formula. You find that sigma times epsilon is sigma, and epsilon times epsilon is the identity. Okay? These fusion rules, again, what they tell you is that if, in pictorial way, it tells you that if you multiply 2 representations, sigma with sigma graphically, it tells you who can propagate coming out of it. Okay? So in this case, you can either propagate the identity representation or the energy representation. Okay? These are not Feynman diagrams. It's just a statement of a product of representations. Okay? This will be important because I will start drawing some pictures like that very soon. Don't confuse them with Feynman diagrams. They are no Lagrangians, they are no Feynman diagrams. So that's good. Okay, so now what we want to do is compute the 3 and 4-point function. Now, let me remind you about this notion that we had of the OPE. So we had this notion of OPE, which is central to the subject. And in the last homework, you will explore some of the important consequences that the OPE has in conformal field theories, which is very special to see. The OPEs exist for any field theory, but for CFTs, they're especially powerful. And you will see why in the homework. Yes?
What do you mean by?
I mean that if you have 2 representations, okay, maybe it's better this way. If you have 2 representations coming in, one labeled by sigma and the other one labeled by sigma, the only representation that you can get on the right-hand side, it was not related to this picture now, but anyway, you can either get only the identity. So these are like Clebsch-Gordon coefficients. It tells you essentially which representations can appear when you multiply 2. So the only non-trivial Clebsch-Gordon coefficient that you can get is sigma sigma 1 from here, or sigma sigma epsilon. Should I elaborate more, or? I can elaborate more, but it's just a picture that tells you, it's a graphical way of describing this. Nothing more, nothing less than that. Okay, so here, when we wrote the two-point functions, I already chose a specific normalization for the two-point function. I said that the coefficient of the two-point function of sigma and epsilon is 1, right? So that means that we already specified a certain OPE coefficient. So let me tell you again what this OPE coefficient was. This was the product of OI, say at Z, OJ at 0, it tells you this was the picture. So you have an operator here, OI, an operator here, OJ. You can have operators elsewhere. So this is an operator relation. This is something that is true inside correlation functions, but we can focus locally here, even though there can be other operators far away. And what this equation tells you is that you can replace, if you are looking from sufficiently far away, the product of two operators by an infinite sum of operators, okay? Which are these OK0. TheseCij's in conformal filters are just constants. They essentially encode the information about the three-point function. That should be clear because the reason that this essentially specifies information about the three-point function is that I can multiply both sides of these equations by, say, OK, and look at the vacuum expectation value. This guy will give me, or OK, let's do OKL. So let me multiply both sides by OL, right? Here, the two-point function of OK with OL gives me delta KL. And on the left-hand side, I get the three-point function, okay? So these Cijks encode the same information as the three-point functions. And if you want to keep track of the Z dependence that this thing has, this is completely fixed by translational, dilatational, and rotational invariance to be HK minus HI minus HJ. Now, something to keep in mind is that when I write this OK is a primary operator, but when you do the OPE of two operators, you get the primary plus all the descendants, okay? So you get plus all descendants. And that's something that you've already seen, like when you did exercises with the free scalar field, when you did the OPE of, say, the stress tensor with X, you got some primary operator on the right-hand side, but then you got all of its descendants, okay? So this is just a statement that when you fuse two representations, you get a certain set of representations with all states in the representation. But all states of the representation are precisely the descendants, okay? You get the primary and all the descendants, okay? Good. So given that we have normalized things in this way, this thing immediately tells us, by chosen normalization, that the fusion coefficient, or the three-point function of sigma sigma with the identity is 1. And the three-point function, or the fusion coefficient of energy with the identity operator is also 1, okay? And these are just fixed by my choice of normalization of the two-point function, okay? Remember that all that I did here is take, schematically, I just take sigma times sigma equals 1 plus epsilon. And all I'm doing is multiplying by, in this case, by the identity and looking at the expectation value. This gives me the expectation value of the identity is 1, and the expectation value of epsilon is 0. So you get precisely that, this and then that. Okay. Good. So the only three-point function left to determine is essentially this one, the sigma sigma. The way we will compute this is by doing something that a priori seems a bit strange. We will extract the three-point function coupling sigma with epsilon by computing the 4-point function. Okay, so we'll compute the 4-point function, and it should be clear why, because I'll go back to it later. So we'll compute the 4-point function and then analyze the 4-point function in a certain limit, and we'll do what's called factorization of the 4-point function that will expose in some intermediate channel. When you think of the 4-point function from the Hilbert space point of view, you will be able to identify precisely which states flow, and then we'll be able to read off precisely what this coefficient will be. Okay, so that's what I want to do now. So just to anticipate where we're going. The reason that computing the 3-point function directly here is not very illuminating is that we already got as much mileage as we could from the fact that of these null vectors. The null vectors acting on the 3-point function there gave us the fusion rules, okay, but didn't tell us the coefficients. So in order to get non-trivial dynamical information, we have to look at the 4-point function, where the differential equation that follows from the fact that you have null vectors gives you is non-trivial. Okay. So now the question is, how much details should I give you about this? I mean, okay, so I'll tell you the logic of how this sausage is made, and the details are. I think that I'll explain all the conceptual details that you will need to do in order to get to this answer, and I will not do all the calculations in the blackboard because it's just manipulating derivatives, and it will not be very illuminating that I do it in front of you. But hopefully it will be clear what the logic of the construction is. Okay, let's go here. Okay, so what I want to do is to compute the 4-point function of the spin operator. So now I'll have to be careful and keep track of holomorphic and anti-holomorphic sites. Okay, so in one of the things that we did earlier in the course is we uniquely fixed the position dependence of this correlator using the word identities. Unlike the 3-point function, the position dependence of the 4-point function is not completely fixed. It depends, it's a function of one cross ratio, remember? So let's write a parameterization of the 4-point function where now we're going to use the fact that sigma has dimension 1/16. So there was a part that was quote unquote boring, which was just fixed by scaling variance. Okay. So this is the part that's completely fixed by scaling variance, times a function of x and x bar, where x was this cross ratio, which was a linear combination of, is a function of the 4 points that you can make, which is invariant under the global conformal transformation. And x, remember, was Z12, Z34, Z13, Z24. Okay? Does this sound vaguely familiar that you've seen before? So remember that we showed that in that 4-point functions? Yes. Sorry? Oh, over here I missed something, yes. This for one, yes. This was the basic statement that we extracted from this study of conformal weight identities, which was that for 4-point functions and beyond, the position dependence was not completely fixed, but it depends on cross ratios. And for the 4-point, there is only one cross ratio, which is this one, okay? So now the question is, how can we compute this 4-point function now? So does someone have a strategy of how we would extract this 4-point function, given what I've been discussing in the last 3 lectures? What's special about sigma? Well, sigma, yeah. About what's special about the primaries of any minimal model? Okay, but yes. So, but the more precise statement is that sigma has a null vector in its representation, right? It has a level 2 null state. And therefore, the null state associated to, say, this sigma will have to have 0 correlation function with all these other 3 sigmas. Okay, so let's do it in 2 steps. I mean, it's exactly the same logic that we use for the 2 and the 3-point function. So here we had a particular level 2 state. So we're interested in this guy, but I'm going to start considering first this guy. Okay, and use the fact that this guy is the level 2 descendant that we know and love. Associated to sigma, which sigma is the 1-2 operator, yeah. So to a primary which has weight okay. And this state is the one that we wrote before, something like L minus 2 minus 3 over 2, 2h, 1, 2. Okay, I don't remember, but some number here. L minus 1 square acting on sigma, okay? So that's the first step. This guy is orthogonal to everyone, in particular to the 3 primaries sigma. Now the second step is okay, and this is 0, is to really say that this guy is orthogonal, which means that the correlation function of the associated operator with everyone else vanishes. And now we use the formula that we discussed many times, and I think Anna derived for you very carefully in the Blackboard, which is that now we can replace this correlation function can be written as, using the operator state correspondence, as a differential operator acting on the 4-point functions of the guys that we really care about. I guess here I want to put a 1, yeah. Okay, and this is a differential equation that we studied for the 3-point function to extract the fusion rules. Now that the differential equations that we're going to get from this is going to be much more interesting, because now the differential, unlike the case of the 3-point function in which the position dependence was completely fixed, so the only information that the null decoupling equation, which that's the name of that thing, could give us is just the selection rules for the fusion. Now the differential equation depends on an unknown function of x, okay? So if we write the formula that for this null vector as a differential operator acting on that, this will give us a non-trivial differential equation for this f, okay? Which a priori we know nothing about, okay? So from here, yes? Yeah, so in 2 dimensions, if you have 4 points, if 4 points are lying in the plane, the other cross ratio is not independent. So you can show that I think it's x. That cross ratio will be x divided by 1 minus x, something like that. So in 4 dimensions, sorry, in 2 dimensions or in higher dimensions, if all points are restricted to a plane, there is only one independent cross ratio. But that's a good question, yes. That's why we can deal with, that's a good thing, because then we can deal with ODEs and not PDEs, which PDEs scare me, ODEs also scare me, but I can deal with them. So from this, we're going to extract an ordinary differential equation for this function f. We're going to find the most general solution to this differential equation and then impose physical consistency conditions to uniquely fix it, okay? Now, the thing that is probably not very illuminating that I do is we gave in class an explicit formula of L minus hat. This was a second-order differential operator that acted on the points of the 4 operators here. So all that you have to do really is plug in that second-order differential operator and act on this beautiful thing. And that will give you a differential operator for f of x and x bar, which I will just write down, okay? I know that you can do at least as good and probably better than me this calculation of how to go from here to the differential equation for f. I don't need this anymore, so I think I can erase it. Yeah, I think I can erase it. Sorry? Okay. So let me take 1 second. Okay, so let's write down the ordinary differential equation associated to this 4-point function of spin operators, okay? So this guy will satisfy this equation, and then I'll tell you some features of it. So it's second order. The reason it's second order, it's clear because the null vector has L minus 1 squared. Remember that L minus 1 is represented on an operator as a derivative. So it will be a second derivative, second order differential equation, plus 1/2 minus x d dx plus 1/16. And this follows without any complication from just writing down carefully what L hat is acting on that sausage. And so let me make a few comments about this kind of differential equations. So whenever, and this is true of not only the Ising model, it's true for when you study general minimal models. One thing that's nice about them is that whenever you apply this game, namely, I mean, one defining property of the Ising model, of the minimal models, is that all primaries have null vectors in them. So I can use the same trick always. I can always write down the correlation function of any set of primaries is killed by some differential operator that you construct from the corresponding descendant. And the kind of differential equations that you always get by doing this game are hypergeometric differential equations. And these are the type of equations that fortunately we know how to solve, okay? So what are some basic qualitative features of this differential equation? Now, it will happen that for the case of the Ising model, where I used explicitly in getting these numbers, 1/2, 1/16, and so on, I used explicitly the fact that the 4 sigmas, each sigma has dimension 1/16. So that's why you get this coefficient 1/16. This 1/2 comes from taking a few derivatives with 1/16 in the denominator and so on. Something that's important to say about these hypergeometric differential equations is that they have 3 singular points. So let me write more generally what the type of differential equation that you would get for any minimal model that has a level 2 descendant. You would get an equation of this type. So you would find that should I write more about this or? Okay, so this is the general form of the hypergeometric differential equation. Some basic properties of the hypergeometric differential equation. It has 3 special points. They're called 3 singular points at x equals 0, 1, at infinity, okay? Oh, yeah, sorry. Thank you. It has 3 special points, x, 0, and 1. Around each of these points, so, okay. Now, around each of these points, the hypergeometric differential equation has a conversion power series expansion, okay? So around each of these points, there is a conversion power series expansion, there is a conversion power series expansion, and there is a conversion power series expansion, okay? That you can write, for example, near the origin. So now I'm winking it because I didn't write this, but in the origin, and someone can correct me if they remember, the conversion power series that you can get just by plugging in a power series ansatz into here is something like that, where these ANs, they're called the Paul-Hammer symbol, which is essentially, I think, something like gamma, the Euler gamma function of A plus N divided by gamma of N. So this is the hypergeometric series, which is a solution of the hypergeometric differential equation around the origin. One of the solutions, okay? And we will come back later. So the fact that you have a conversion power series around 0, 1, and infinity is very strongly related to the fact. So the fact that you have convergent power series representation is physically related to the fact that the OPE has a finite radius of convergence. The OPE in conformal field theory has a finite radius of convergence. So now I'll draw some pictures. Hopefully they're useful. If they're not useful, forget them. Now, another way you could, and this will be the logic that will lead us to this guy, to the 3-point function. One way you could have computed the 4-point function is by using the OPE, okay? So how would you have computed the OPE? So you have 4 operators. What you want to do is collide pairwise 2 operators, decompose the OPE of each pair of operators into a sum of other operators, and that gives you the 4-point function. So pictorially, there are 3 ways of doing this. One that we can call the S-channel factorization of the 4-point function. And this is in the limit where we take Z1 very close to Z2 and Z3 very close to Z4, okay? So this is the operator at location 1, 2, 3, and 4. This picture is describing factorization of the 4-point function, where you bring operator 1 and 2 together. Now you use this OPE. So this was this picture, right? So I have operator OI JK, okay? So in this factorization, what I'm doing is I'm bringing operator 1 and 2 together. I decompose in terms of all the operators that can appear in the OPE of sigma with sigma. I do the same thing with operators 3 and 4. And then all that I'm left is the 2-point function of the operators that you get from the OPE here with the operators you get from the OPE here. Is that clear? So one nice thing about conformal field theories is that by using the OPE one time after the other, you can always reduce the correlator of n operators into sums of pieces that you construct from the 3-point function and the knowledge of the spectrum of the theory. Because all that we used here is that you can reduce the 4-point function into, by doing the OPE of 1, 2, and 3, 4, into these fusion coefficients associated to 1, 2, and 3, 4, times the 2-point function of the operators that are flowing in here with the operators that are flowing in here, okay? Now, if you do this thing, if you do it in this channel, in the S channel, since you're taking Z1 near Z2, where did I write the cross ratio? Yes, so the cross ratio is there. That means that you're representing the 4-point function as an analytic power series in X, because Z1 is approaching Z2, and therefore X is small. Another channel that you could have computed the OPE is in the T channel, where now you collide operator 2 with operator 3 and operator 4 with operator 1. Can people see? So you do a different factorization. You have 4 points, and there are three different ways in which you can bring 4 points pairwise together. So here you do the OPE of 2, 3 with 1, 4, and then you're left with a 2-point function of the states coming in here and coming in here. This will give you a power series representation in X, so near the origin. This will give you a power series representation in 1 minus X. Because now, well, if you look at that formula, if 2 approaches 3, you're expanding in 1 minus X. And the last one, usually I run out of space, it's called the U channel, where now 2, so here 2 collide with 1, here 2 collide with 3, now I can collide 2 with 4. And since now 2 is approaching 4, you get a power series in 1 over X, okay? So so you can think, this is crazy. We're talking about the same 4-point function. How come I get 3 different answers? And the point is that they're not different answers, they're the same answer. And the point is that you have the correlation function is an analytic function in the complex plane that have a power series representation at these 3 special points, 0, 1, and infinity. And these solutions that you get around each of the different points are related to each other by analytic continuation, okay? So there's a unique solution with 3 different power representations, but it's the same solution, okay? And physically, this is very important because one of the basic assumptions of CFT, and in fact, that's another way of thinking about how to solve CFTs, is the picture of so-called associativity of the operator product expansion. That's just the statement that it shouldn't matter. So if I give you a 4-point function, the result of the calculation should not depend on whether you compute it in the S channel, T channel, or U channel, okay? One way to think about that is that you have OPEs, which are the way you multiply operators when you bring them together. But when you have multiple operators, it shouldn't matter in which order did the OPE. It shouldn't matter whether I do one OPE to 3 or 1, 2, then OPE with 3, okay? So one of the basic consistency conditions and this is true in any dimension. It's true even for non-minimal models. Okay, this is true in 4 dimensions for any consortium polynomials for any CFT. Is that the OPE is associative, which is just this statement. Well, it's stronger than this statement because here I'm just talking about the 4-point function. If you were doing the 75-point function, you could factor that out in a gazillion numbers of ways. But associativity tells you that it shouldn't matter, the answer, and that different ways of factoring are related to each other by analytic continuation. Okay? And the fact that, for example, this correlation function computed this way and computed this way have to be the same, provide very strong constraints on the CFT. And in fact, you can determine some information in 2 dimensions, a lot of information, in higher dimensions, less information about the CFT by imposing as a physical consistency condition the fact that correlation functions should not depend on the way you factor them. And by, for example, equating the result of the computation performed in the S channel and the T channel allows you to extract information about the spectrum, for example. Okay? That's something that's quite popular now in higher dimensions. And that's how people are starting to get some information about the spectrum of CFTs in 4 dimensions that don't have Lagrangians, just by imposing these consistency conditions. Hopefully that wasn't too crazy or abstract, but you never know. Okay, so now the thing that's very fortunate about the Ising model is that in general this thing is nasty. I mean, in general, this guy only has a power series representation around, or you can give it an integral Mellin-Barnes representation of the solution. For the case of the Ising model, the differential equation that I wrote somewhere, I thought I did. Okay. Has an elementary representation in terms of rational functions. Okay. So now we're going back. So after this detour, I just wanted to explain to you a little bit more about the OPE, and you will do some exercises to reinforce its importance in the tutorial, in the homework. And also we'll come back to it when we try to get the 3-point function. But now I want to complete this analysis of the 4-point function of the spin operators. No, I don't want to erase this one. I can erase the other one. So this is a second-order differential equation. So there are 2 independent solutions for this very particular differential equation for the Ising model. They're elementary. So there are 2 solutions. So let's call them F1. And F2. Like that. Now, this, as I said, so just on the general theory of hypergeometric differential equations, these functions have convergent power series expansion around 0, 1, and infinity. For the lecture today, I'm going to only use a little bit the form of the expansion near the origin that will be used. We will use it when we study the behavior in the of the 4-point function in the limit that x goes to 0 that corresponds to this factorization channel, okay? So f1, if you expand this, and you didn't make a mistake, you get root 2, 1 plus order x, and f2 of x, the 1's cancel, so it's higher order already. So root x over root 2, 1 plus order x, okay? So this is near equals 0. So we found the most general solution to the hypersymmetric differential equation. I wrote the differential equation coming from the holomorphic side. There's an identical differential equation acting on x bar. So at this level, the most general solution of the correlation function is given by this. So the 4-point function takes this form. So it has this not super exciting piece. And now we have to write down the most general solution and the most general expression for f, okay? But since we know the two solutions, and we know that there is a differential equation acting on holomorphic on x and x bar, the most general solution is ij equals from 1 to 2. There, the second order equation, we have two solutions of a matrix of functions ij that we don't know anything about yet, times fi of x, fj of x bar, okay? So let's see. This is not an easy question, but it will make me very happy if you can give me the answer. So, what do you think is the physical interpretation of these two terms in the sum? So imagine you expand this near x equals 0, then you're doing the OPE of sigma with sigma, right? And then what we're saying is that in this, when you factor it in this way, you can write the correlation function as the sum of two terms. Yeah, so the way to think about that is to remember the fusion rules of sigma with sigma. So sigma with sigma gives me 1 plus epsilon, right? So if I factor the 4-point function like this, I have sigma, sigma. The guy that can appear here is either 1 or epsilon, right? So each term in the sum here is giving you the contribution to the 4-point function. One coming from the term in which the operator that exchanged in the OPE of 1, 2, and 3, 4 is the identity operator. That would correspond to F1. And the other one is the contribution to the 4-point function associated to the contribution of the states that associated to epsilon, which appear in the OPE of sigma with sigma, okay? These guys, this way of writing correlation functions as sum of, okay, for minimal models, it's always a discrete sum. For more fancy CFTs, it could be an integral. But the way of writing this object here, so that you know, it's called a conformal block, okay? So this guy is something like f1 of x, this is f2 of x, just so that in case you hear a name, they're called conformal blocks. They essentially encode the complete information contribution to the to the 4-point function of all the states associated to a given intermediate channel, or primary, in this case epsilon, summed over all its descendants. Because when I write it here, remember that I said when you do the OPE, you get the OPE of two operators, gives you a sum over primaries plus all of its descendants, okay? So these functions f1 and f2 are summing up the contribution to the 4-point function to all states, including the descendants associated to this particular primary that appears in the OPE, okay? So now, how are we going to determine? We're still not done. We have to determine this coefficient, this matrix Aij, and now that's where we use a physical requirement. And I will explain how to do it. I will not do the analysis because it's straightforward. You can try to do it. Essentially, what you want to do is that you want to impose. Sorry. You want that? You want to say that the correlator should be single valued. Okay? That's the statement that it shouldn't matter if I have the 4-point function. You should get the same answer whether I move one operator around the other one or not. Okay? Now, in order to answer these questions, then what you have to do is the following. So I said that for hypergeometric differential equations, there are 3 special points, 0, 1, and infinity. Another important property of hypergeometric differential equations is that 0, 1, and infinity are branch points. So that means that if I take a solution, a basis of solutions to the differential equation, say around the origin here. So here I have f1 and f2. But now I do a contour in the complex plane encircling the origin, which is a branch point. What typically happens is that this basis of solutions acquires a monodromy, which is just a statement that upon going around this point, f1 and f2, since obviously doing a monodromy should give you back a solution, you have to get a linear combination of the original functions. So what you get is a matrix, omega naught. So let me write alpha, beta, gamma, delta, acting on f1 and f2, okay? And this is called the monodromy matrix as x goes e to the 2 pi I x. So when I take x and I go around the origin, okay? And for example, in this particular case here, so let me just do this very particular example. Let's compute what the monodromy matrix associated to the solutions near the origin would be. So if I take x, so this is the behavior of the solutions near the origin, right? Now let's take the solutions and move it around the origin. So let's evaluate f1 at 2 pi I x. What do you get? Well, you get back f1. So in this case, you don't do anything. But what happens to f2? You get a minus sign. So in this case, the monodromy matrix omega naught is just 1, 0, 0, minus 1. Now, in principle, what you have to really do is check what is the monodromy transformation properties of f1 and f2 around each of the 3 branch points, okay? And pick the linear combination that's going to be single valued, okay? That's going to be invariant under these monodromies, okay? And from here, by doing this analysis more carefully, it's already pretty clear what it has to be. It will just be the complex conjugate, the sum of the diagonal pieces of f times its complex conjugate, okay? So from here, we're going to get that the correlation function, the 4-point function, will have to be this times a constant A that we still don't know, times the sum from 1 to 2 of fi x squared, which is obviously single valued. Well, no, at least around the origin it's obvious. Around the other points you have to check, but it's true. Okay. So we have determined, this is amazing already, so we have determined the expression for the 4-point function up to a constant A that we have not identified. And F1 are very explicit functions, okay? And as I said, they correspond, they are the conformal blocks associated to the Ising conformal field theory. And now what I want to do is to go back to the thing that we didn't finish, which was the calculation of this 3-point function, sigma, sigma, and epsilon, okay? And after all this speech that I've been giving, it should be clear that what I have to do is now look at the exact 4-point function and factor it in the S channel, because then when I factor in the S channel, I will get a sum of two pieces, one in which the OPE coefficient here will be sigma, sigma times identity, plus another contribution where the OPE coefficient will be sigma, sigma, and epsilon, okay? And by comparing the two expressions, we will extract C sigma, sigma of epsilon, okay? Okay. I'll try to be done soon. I'll be done soon because I'm running out of steam, of voice more than anything. Okay, so now we want to look at the OPE of sigma with sigma. Let me write it more explicitly what it is. And let me keep the leading order terms in the OPE, okay, the most singular terms. So there are two primaries that can appear here, right? It can either appear the identity or epsilon. For the identity, we just get 1 over Z12 to the 1/8, Z12 bar to the 1/8, times identity. Here, a priori, I should have, what should appear here is C sigma, sigma the identity. But this, with our choice of normalization for the 2-point function, was 1. And then the other term that can appear is C sigma, sigma, epsilon, Z1/2 to the 3/8, Z1/2 bar, sorry, to the 3/8 times epsilon Z2, Z2 bar, plus descendants, right? So can someone tell me how I got this number, 3/8 here? Okay, let's see. So, yes. Did people see what I did here? So that I said that in the OPE, when I use the OPE of 2 points, the usual symmetry is fix the position dependence, right? So it was Z to the HK minus HI minus HJ, okay. Right? So here, I'm using the fact that these operators have dimension 1/16, 1/16, 1/16, that epsilon has dimension 1/2. So here, in this particular case, okay, that was kind of boring. We have Z to the minus 1/8, right? Because we have 1/16 plus 1/16. And here you have exactly as Aitor said. Okay, so that this is hopefully clear. I lost my eraser. So I think I can erase this. Now, now let's compute the 4-point function from the OPE point of view. Okay, remember that I said that I can compute the OPE. So I compute the 4-point function by sequentially doing the OPE in 1, 2, and 3, 4. And for the time being, let's look at the leading order terms as x goes to 0. Okay, so here is doing the OPE on this side. I have, of course, if I want to compute the 4-point function, I have to compute the OPE on this side and glue them together. Okay. So the 4-point function computed from the OPE. So let me call, so I don't have to, okay, let me write it like this. So bracket, so the 4-point function will be times C square sigma sigma the identity. But remember this was 1. So this is the contribution, the leading order contribution to the 4-point function from this channel. So what I have to do is put together the leading OPE expansion of these two guys, which is this, times the OPE expansion of these guys, which now is exactly the same as what I have here, but of course, the locations are now at 3 and 4 instead of 1 and 2. And here I just use the fact that the 2-point function of the identity is 1. Okay. So this is the contribution from this conformal block. The conformal block where you exchange the identity between the external legs. And now I have the contribution from the other conformal block that we're interested in, which is the one that contains the energy operator. So here we know what we get. Divided by okay, can someone, so it's clear where these terms came from, right? They just came from the OPE on one side of the diagram, the OPE on the other side of the diagram, 1, 2, 3, 4. Where did this come from? Sorry? Precisely. So do people understand that? So when I do the OPE, the whole point of the OPE is it allows you to reduce a higher point function essentially to 2-point functions. Okay? So here what we did is to fuse sigma with sigma to get epsilon here and epsilon here. So the correlation function essentially reduces to C sigma sigma epsilon times these crappy terms that I'm not worried about, times the 2-point function of epsilon with epsilon. Epsilon at Z4 and epsilon, which arises from here, times epsilon at Z2, which arises from here. And this guy is 1 over, hopefully, Z to the 4 square. Okay? Good. Plus, of course, higher order terms that for the time being we're not interested. And again, the picture here is that this is the contribution from this channel, and this is the contribution from this channel, from this exchange. So in the CFT, we can always look under the hood and in any given correlation function, see which states are contributing to each term in the correlator. Okay? So in the first term is the contribution from the identity and its descendants, and here is the contribution of the energy operator and its descendants. Of course, now here I'm only keeping the leading term, but in principle, you have to keep all of them, and we know how to keep track of them. We know the explicit form of the conformal blocks. So now what I want to do is I computed the 4-point function of the spin of the 4 spins from the point of view, from the OPE point of view. And of course, this has to agree with this, because we're computing the same quantity in 2 different ways, okay? So now I have to compare this result. So now let's look first at this term. Versus the form from the correlator. So from the form of the correlator, all that I have to really do is look at the leading order term in the expansion here. So here I conveniently wrote what F1 and F2 do as x goes to 0. The leading order term is only F1, right? Because F2 is suppressed as x goes to 0 with respect to F1, okay? So the correlator in the limit that x goes to 0 okay, well, it gives me a factor of 1/2. This factor of 1/2 is just this factor of 1/2. Sorry, I'm looking at the wrong place. No, so here I get a factor of a. Sorry. And if you're careful about taking the limit 1, 2 to 3, 4 from that formula, what you will get precisely is yeah, so that's the pattern B. Yeah, so you have okay, 2a times precisely, if you're careful, z 1/2 to the 1/4 times z 3/4 to the 1/4. That's the leading term in the expansion around x equals 0. Only F1 contributes. But this guy has to be the same as this guy. So from here, we fix the overall normalization of the correlator to be a equals 1/2. Good. Now, what's left to do is to work a bit harder and keep the next two leading order term. Because if you want to fish for this term, the sigma sigma epsilon term, we have to expand, we have to keep essentially information about F2, the next two leading order term, okay? And so now look at subleading term. From correlator. So just write down. I mean, it's completely straightforward. There's not much point in me doing it in front of you, but essentially the only thing that you have to be careful is about just plugging in this extra factor of x here, square root of x, and comparing. Now, given that we know now that a is 1/2, looking at the second order term here and comparing with this, you will get that C sigma sigma energy equals 1/2, okay? So you see that by using the special properties of minimal models that, and in particular the Ising model, that they have null vectors under each of its primaries, we wrote down a differential equation using the fact that any CFT has a OPE, a conversion OPE. Yeah, so, okay. Well, you will see in the homework what the statement about convergence of OPE really means. You will show what is the radius of convergence, in fact. So just using this simple criterion, we have essentially determined all the 3-point functions and the 4-point function of the spin operators. And the thing that's remarkable is that using fairly simple techniques, one is able to write down formulas that people doing much harder work in the lattice were able to compute by solving the model exactly there. So that's very rewarding. And essentially, I can essentially stop just by saying that if we wanted now we could compute other interesting correlators. Instead of the 4 spins, we can compute, say, the 4 energy operators. And what you would have to do would be conceptually very similar to this. Of course, now the null vectors associated to the energy operator will be slightly different, but conceptually there is nothing new. And I would say there is really nothing conceptually new when you look at more complicated minimal models. What will happen typically is that instead of getting a second-order differential equation, you might get a higher-order differential equation because the null vectors are at a higher level. But I hope that at least with this simple, well, it's not completely simple, but with this particular example, that now you will be able to, if you really want, be able to essentially compute the correlation function of any minimal model if you ever wanted to. And more importantly, that this is just a small view of the kind of many applications that CFT can have for statistical physics, but also for other areas of physics and mathematics. And hopefully you find that interesting. But I want to finish you with wishing you good luck in the rest of the year and beyond that. Thank you.
Thank you for making the effort these last 2 days.
Oh, no problem. I think I have so many of those already. Okay, thank you. Is it cash? Oh, thank you very much. Thank you, guys.